Hello, everyone. Thank you for tuning in. My name is Veronica, and I'm part of the Math 32 Section 11 discussion for the 2020 fall semester. Today, I will be going over jitter plots. You may ask, what do you mean by jitter? Well, we all know the jitters you get when you had one too many cups of coffee. However, that's not the jitter I'll be talking about. Instead, I'll be going over jitter dots. As you can see, these jitter dots are simply a multitude of marks displayed on a graph to represent different data. The use of jitter is a great technique in dot plots, box plots with dots, and even scatter plots. Jitter is typically a random value that is assigned to the dots to separate them so that they don't overlap. So now that we know what jitter is, we can ask the next question. What is the jitter plot? The jitter plot is a visualization that allows you to clearly see the distribution of the data. It also helps you compare the value for the two variables on the same scale. According to the Data Plus science, these jitter plots are useful because they subtly highlight the comparison of the two variables for specific points. As you can see from the graphs on the right, the specific points are compared with a red connecting line. Jitter plots are also helpful since, as mentioned earlier, the distribution of marks avoids any stacking or any sort of overlap. Jitter plots should be used when you want to spread the dots in your distribution when they are tightly packed, for it'll make your data easier to read. This jitter technique also allows you to separate marks into different columns. You should avoid using jitter plots when the exact location of a mark is important for the analysis. An example could be when you're working with geographic data. If, for example, you wanted to measure when and where gas emission were to be detected by a sensor, the jitter plot would move overlapping marks to other spots within the vicinity, therefore giving you less accurate data. Now, let's look over a real-life example with data provided by the well-known sports coverage channel ESPN. ESPN ranked the top 60 most physically demanding sports. They were each evaluated by 10 different attributes, including agility, durability, power, speed, and strength. Each sport was assigned a value from 0 to 10 for each of these attributes. And once the data had been collected, analysts input this set of information into a plot. This is the end result. As you can see, the x-axis is composed of each of the 10 attributes, all which have their own neatly spaced column. The y-axis is scaled from 0 to 10, allowing the jitter to be graphed accordingly. The stacked rows to the left all represent a different sport. Now, the higher the row is placed, the more physically demanding it is. If you want to know more about a given sport, you can click on one of these rows. The corresponding dots will become highlighted, allowing you to see the specific values. In this case, you can see that baseball, softball, was ranked number 9, scoring 62.3 out of 100. To those who are curious, according to 8 expert panelists, boxing was ranked the most physically demanding sport. It scored exceptionally high in power, endurance, agility, speed, strength, and of course, hand-eye coordination. Now that we went over our example, I hope you can begin to see how useful jitter plots can be. These graphs are important because they are a common method to visually illustrate relationships in the data and establish concrete comparisons. As with most other graphs, their purpose is to present calculations and numerical patterns that are too complicated to be described properly through text. Overall, jitter plots are an effective tool to simplify our data. And lastly, the jitter is an eye-catching approach that can provide us with a useful presentation visual. Here are the references used for research purposes of this project. And with that being said, we've reached the end of this presentation. Thank you for watching and have a great rest of your day.